Hello and welcome to our lesson on the pH scale for higher tier students only. So far we've looked at the pH scale. You should recognise this. You should know the colours and the numbers. You should recognise neutral is in the middle. As we get further away from neutral down to 0, it's becoming stronger acid. And as it's going further away from neutral towards 14, you're getting a stronger alkali. We've just had lessons, or we've just done 2 lessons on strong and weak acids and then concentrated and dilute acids. But how do they affect the pH scale, or what does that look like on the pH scale? Well, the rule for the pH scale is that the higher the concentration of H+ ions, the lower the pH. Okay, the higher the concentration of H+ ions, the lower the pH. So if I show you this picture here, I've got a strong concentrated acid. Where is that going to be on the pH scale? Well, hopefully you would recognise it's going to be all the way down here. There is a high concentration of hydrogen H+ ions in this strong concentrated acid. What about this one? Well, this is weak and it's dilute. So weak, only partially ionised, and dilute, there's not many particles in a given volume. And so the concentration of hydrogen ions, there's not many of them. So it's going to be a weak acid. Okay, what about this one here? It's a strong acid, so all the hydrogen ions are ionised, but it's dilute. So there's not actually many particles in a given volume. Well, hopefully you could accept that it's still going to be relatively strong, but it's not going to be as strong as that concentrated acid that we had previously, because there's simply not as many or not as concentrated number of hydrogen ions. So it's not quite as low as the previous one. Okay, what about this then? It's a weak acid, which means it's only partially ionised, but it's concentrated. So there's actually a lot of particles in a given volume. Well, hopefully you might put it somewhere around here, similar to the last one. Yes, it's weak, but actually because it's concentrated, we actually have a reasonably high concentration of H+ ions. There's quite a lot of them, and therefore it's quite a low pH. And this is the misconception I want you to pick up on. A weak acid could still have a low pH if it's concentrated enough. Okay, so the next thing you need to know about the pH scale is it's logarithmic. Now this means that instead of going up or down in ones, so 1 extra hydrogen, 2 extra hydrogen ions, 3 extra hydrogen ions, if we did it to 1, 2, 3 scale, this scale would be absolutely massive, because the number of hydrogen ions is mind-boggling. And so we have to have a logarithmic scale. Now what this realistically means is if I start at neutral, this jump here between 6 and 7 is 10 times as many hydrogen ions. So there are 10 times more hydrogen ions in pH 6 than there are in pH 7. And so we've dropped down 1 pH value, but we've increased by 10. Now, if I went down to pH 5, I've actually gone 10 times 10 times. And therefore, 5 compared to 7, or pH 5 compared to pH 7, is actually 100 times the concentration. There is 100 times more hydrogen ions in pH 5 than there is in pH 7. And I could go on. This one here, if I'm jumping down to pH 4, 10 times 10 times 10, you're looking at 1,000 times more concentrated than pH 7. So this is what it means to be logarithmic. So what would that actually look like? So here's a worked example. It says at a certain dilution, the hydrogen ion concentration is 0.001 moles per decimeter cubed, and the acid had a pH value of 3. If we increase the concentration of hydrogen ions, so that's going to make it more acidic, which means it's coming down the pH scale. If we increase the concentration of hydrogen ions to 0.1 mole per decimeter cubed, what is the new pH? Okay, well, how do we get from 0.001 to 0.1? Well, we're going to times it by 100, so we're moving 100, which we know then is increasing the concentration of the pH by 2. So we were at pH 3, so we're now going to be at pH 1. Okay, I'm hoping that makes sense for you there, guys. Okay, so let's look at this question. I suggest you pause the video and have a go for yourself. Okay, so this one is one that's going to catch you out if you've not learned those core concepts. It says, which of these is the best explanation for what is meant by a strong acid? So all of these answers are correct in some way, but some of them are strong, one of them's weak, one of them's concentrated, and one of them's dilute. So you've got to really know your definitions. So A, there's a large amount of acid and a small amount of water. Well, that's not strong, is it? That's concentrated. Okay, so B, there's a small amount of acid and a large amount of water. Well, that's dilute. C, the acid is completely ionized in solution in water. So I think it's going to be C. And D, I'm going to double check, the acid is partially ionized. Well, yes, okay, that is going to be weak. Okay, so the answer is C. Okay, so for the next few slides, the question, it all starts with the same part of the question. So this is all part of the same big question. So I've kept this picture and this table on each slide so you can look at it. But pause the video and have a go. Okay, so first of all, it says explain why phosphoric acid is described as a strong acid. Well, we know what a strong acid is, don't we? So the H plus ions are completely dissociated. Now, interestingly, if you look at the answer from the mark scheme, I just want you to look at the ignore bit there. It says ignore strong acids are more ionized or dissociated than weak acids. It's not looking for more, completely, all of them. Okay, so be careful. B, explain why the solution phosphoric acid used is described as dilute. Well, what does dilute mean? It means there's a low ratio of hydrogen ions to volume of solution, or there's not many H plus ions in a volume of solution. Okay, pause the video and have a go at this one. Okay, so the answer to this balanced symbol equation should look like this: a 2, a 3, and a 6. The exam is looking, or the exam board, sorry, is looking for 1 mark for the correct balancing of the 2 and the 3, so the reactants, and then another mark for correctly balancing the products. If you've got multiples of this, so if you ended up with 4, 6, and 12, you would still gain the marks. If you didn't understand this, then go back and watch that video on balancing symbol equations. Okay, pause the video and have a go at this for me, please. Okay, so it says look at table 16.1. Whenever it says look at a table or there is a table present, then you're going to get a question, or at least one question, that refers to that data, and you're going to have to use it. So it says describe how the pH of the solution formed changes as the concentration of hydrogen ions in the solution changes by a factor of 10. Okay, so we know that the pH of a solution decreases by 1 every time concentration increases, or concentration of hydrogen ions increases by 10. So let's say that then. So pH of the solution increases by 1 as the concentration of the hydrogen ions decreases by 10. Now that one there is the opposite of what I've just said. It's the other way round, and that's absolutely fine. I've made that point, I've made that connection between the pH increasing or decreasing by 1 and the concentration increasing or decreasing by 10. Now you might think, well, that's me done and dusted. However, there is another part to this question. It says use data from table 16.1 in your answer. So let's look at the table, and I want to prove that if the pH changes by 1, the hydrogen ion concentration decreases by 10. So I've got the pH solution there. I've got 0.5. Well, if I increase that by 1, so 1.5, what's the change in concentration? Well, 0.32 to 0.032. So actually that shows it very clearly, doesn't it? So I would say something like the pH increases from 0.50 to 1.50, whilst the concentration of the H plus ions decreases from 0.320 to 0.032. So I'm showing that from the data. I've said, look, it changes. If I increase pH by 1, the concentration decreases by 10, and then I've proved it using the table. Now, you could have also used the pH 1 to pH 2, and exactly the same thing happens there. So either of those answers would be correct. Okay, so pause the video and have a go at this question for me, please. Okay, so it says the reaction between phosphoric acid and calcium hydroxide is a neutralization reaction. Well, we know all about those. Write the balanced ionic equation for neutralization. Include state symbols. Okay, well, we know what the balanced ionic equation for neutralization is because it's the same every time. And state symbols, well, you'd hopefully recognize that the H plus ion would have to be aqueous in order for it to be an ion. As is the hydroxide, also aqueous, and it makes water, which of course is a liquid. So the very end of this topic is this information about titration curves or titration graphs. Now, if you went on to triple, you'd do this in more detail, and to me it seems strange that they've included this, but you need to know it. And you just need to recognise the shape of the graph. So I'm just going to give you some information, but realistically, the next slide really kind of is all you need to know. So first of all, the end point is where there's a sudden change of pH, and it's that kind of that dip in the line there, that sudden change from about pH 11 to pH, where we're about pH 3 very, very quickly. It's almost a straight line. The pH curve can be used to show pH changes in a titration. Now, a titration is not something you need to worry about. Like I say, it is triple, but all it means is it's a very slow, very precise way of measuring the concentration of acids and alkalis. And the range of pH is where the neutralization is happening, that vertical section. So the range of pH here is from about 11 to 3. So what do you actually need to know about titration curves? So this is it basically. You would need to look at one of these graphs. You need to look at this graph and you'd need to know what you were adding together, whether it was a strong acid or a weak acid, a strong base or weak base. Remember, when bases are alkalis. And it's really simple because look here, it says pH 14. Well, that's a strong alkali, isn't it, or a strong base? And it only gets to here, which is a very weak acid. And so this is a strong base being added to a weak acid. Let's look at this one here. I've got pH 14, which is a strong acid or a strong, sorry, not a strong acid, a strong alkali or a strong base. And it goes all the way down to here. So I must have had a strong acid, otherwise I'm never going to get to pH 1. So this is a strong base being added to a strong acid. For this example here, well, I haven't made it up to pH 14. It's relatively weak here. It's not that far off 7. So I've got a weak alkali or a weak base. But it also does get down to pH 1, so I've got a strong acid. So this is a weak base being added to a strong acid. And here, this one here, again, I've got the weak alkali being added to the weak acid. And that's really it for titration curves. Okay, guys, that is the end of today's lesson, I will see you later.